So we do have one more speaker today, and this is Christian Fredrickson who is a PhD student at Tulane University.
All right, thank you. So today I'm going to talk about Bayesian design of experiments and parameter recovery. So the Bayesian design of experiments is stuff I did last summer at the Virginia Tech National Security Institute, and the Bayesian parameter recovery is sort of the topic of my thesis. So this is joint work with Nathan Glatt-Holtz, Justin Krometis, Victoria Sieck, and Laura Freeman. So the theme of both of these projects is how can we better estimate unknowns? So we've got a parameter theta, and we've got some data, and we're going to assume our data is generated by some function of our parameter theta, and where we collect our data, which is going to be d, and it's corrupted by some additive noise that we're going to call eta. And so we can consider theoretical or empirical models. So our ability to determine theta is going to depend on what we're measuring, which is going to be implicit in the function g, where we're measuring it, which is just d, and how we use our measurements. And so, as you might guess from the title of the talk, I'm going to be talking about Bayesian methods for that last bullet. So I'll start with some DOE. So our starting point was this paper here, case study on applying sequential analysis and operational testing. So in this, they proposed a new sort of sequential DOE methodology, and they used a simulation study to compare its performance to just classical non-sequential DOE. And what they found is that the average number of tests called for by their methodology was lower, so those are the green bars here, than just classical non-sequential DOE, which is the purple bar. And I didn't want to squeeze too much on one slide, but when they looked at sort of metrics that gauged how effective the predictive coefficients were, they found that their methods were just about as good, or I think in a few places maybe even better, than just regular DOE. So what we wanted to do is consider sequential Bayesian DOE. So before I talk about that, just in case no one's ever seen anything Bayesian before, the three key pieces are going to be your prior, likelihood, and posterior. So as the name suggests, the prior is going to capture what you might believe about the parameter going in. So here, that's going to be that blue curve, and the larger standard deviation might indicate that we're initially pretty uncertain about what this parameter is. We're going to have a likelihood function, which is going to relate the parameter, our data, and where we collected that data. So that's going to be this orange curve here. And we're going to combine those using some form of Bayes rule to get our posterior, which is going to be this green curve. So in Bayesian DOE, what you're going to try and do is perform your next test wherever a utility function is maximized. So our utility function is this function un right here. And to compute the utility of a design, we're going to basically average this little u, which is going to be some functional of the posterior, according to our likelihood. And this is either going to be the posterior here, or it's going to be the prior if we haven't yet collected any data. And so wherever that utility is maximized is where we're going to perform the next test. The two utilities that I saw most frequently used for parameter recovery were mutual information and Bayesian de-optimality. So mutual information, you're basically trying to maximize the difference between either the prior and the posterior, or the current posterior and the posterior after your next test. Bayesian de-optimality is not very different from classical de-optimality. We're trying to minimize a covariance, but here it's going to be the covariance of our posterior. So this basically captures what we found. So the y here is the little L2 norm between the true parameters and the parameters predicted in our sort of simulations. And so what we see is that the Bayesian methods performed just about the same as classical optimal design. And the designs were actually almost identical. I think for the main effects only model, they were actually just permutations of each other. So it makes sense that their performance was just about the same. This yellow line is just the performance of, or the average performance of some randomly generated test designs. And we just have that on there as a benchmark to show that optimal design is helpful. And so the conclusion, actually, which was a little disappointing, at least to me, was that for these sort of simpler models, you should not use Bayesian optimal design. Even though you do just about as well as classical optimal design, it was much more expensive to compute these designs. And since we didn't really gain a benefit from that, it's not really worth it. So now I'll shift and talk about Bayesian parameter recovery, which is going to tie back into DOE. So the toy model that we've worked a lot with is the advection diffusion equation. So you can just imagine you have a big bowl of water, and maybe you have some motors in the water that are moving it around and creating some current. So the question we're interested in is if we drop some dye in the water, and then we just observe the dye at a bunch of points, can we figure out what the current's going to be? And so we model that with the advection diffusion equation, and this is going to depend on some initial condition. So these are just pictures of a potential flow and maybe what the dye looks like at some time. So our observation model is exactly the same as before. Now our designs are going to be points in time and space that we're going to call TJXJ. So here our posterior is exactly the same as it was a few slides ago, except now I want to be very explicit that this depends on N, which is going to be the amount of data that we have. So we don't just get one posterior, we really get a sequence of posterior measures. And so maybe the most important question you can ask is how do those measures change as N grows? And so what we see in this image here is what we want to happen, right? As we're getting more data, our distribution is shifting towards the true parameter, and the standard deviation is also collapsing, which would indicate that we're becoming more and more certain about what that parameter is. So when we have this behavior, we say that posterior consistency holds. And so for something like a linear model, you might not really be all that concerned with establishing this. I think maybe you assume if you get enough data, eventually you'll be able to figure out what the coefficients are. But in something like the advection diffusion problem, now the parameter we're trying to recover is really a function that may be infinite dimensional. So we're basically always underdetermined, and it's no longer guaranteed that you have this behavior. And we actually know of several situations where you do not have this behavior. So basically a big part of my thesis and a big part of the work that we've done establishes conditions under which this happens. And I think the biggest contribution of it is that it works not just for the advection diffusion problem that I just talked about, but for an entire class of PDE constrained problems. And then now that you hopefully agree with me that consistency is important, I'm going to tell you two ways in which it's not as good as we would want it to be. So the first is entirely our fault, and that is that our theory is suboptimal. So the set of conditions where we can prove posterior consistency holds is going to be a subset of the conditions where it actually does hold, and it might even be a small subset. So to look at some of those other conditions, we sort of need to run some simulations. The other way that it sort of falls a little bit short is that it's a property that either we have or do not have in a large data limit. But in the real world, we're always going to be in the sort of small to moderate data realm. And consistency doesn't necessarily tell us anything about that. So to look at both of those, we've been doing a lot of simulations with this advection diffusion inverse problem. So a very important question is how do we want to quantify how well these methods are working? And sort of the most comprehensive is root mean squared error. So this is going to capture both the bias, so the difference between the posterior mean and the true parameter, and the standard deviation of the posterior. And then what really ties this back into DOE is that in a lot of our experiments, we've been looking at things that can improve parameter recovery. And so this plot here shows what we found to be the most significant, which is strategically scaling our observations. And this picture is actually pretty incredible because this x-axis is log 4. So what we see, this blue line is unscaled observations. So 4 to the 6 is 4,096. What we see is that 4 to the 4, which I think is 256 scaled observations, actually do better than 4,000 unscaled observations. So that's a pretty remarkable improvement. And just to tie it all together, we have not fully investigated all of this. This is maybe a little bit of a wish list, but but it's plausible enough that I put this in here. So if we have better observations, that could come from strategically scaling our observations or better DOE. We should get a better posterior. If we're using Bayesian DOE, we should get a better utility from that. And then that's going to get better DOE again. If we're using classical DOE, I still think there are lessons that could be learned about both DOE and perimeter recovery from looking at them sort of through the lens of the other. And that's all I have. Sorry.
Thank you so much.